Hi, welcome to my lab report of Lab 2 motion of a falling object. In this experiment, I have dropped this styrofoam cup from some height and I have kept this meter scale for calibration of the distances. You can see the calibration stick, it's a meter scale. I have calibrated it to 1.0 meters. For my graph, for my reference frame, I have kept the origin at the point from where I dropped the styrofoam cup. So this is positive x-axis, towards left is negative x-axis, upwards is positive y-axis and downwards is negative y-axis. I have used iPhone, so it shot the video at 120.2 frames per second. You can see it here, the details. If you go to properties, it's 120.2 frames per second. And you can even see that the frame duration is more or less constant, so all frame durations are equal. So data collection has been pretty accurate and I have got a lot of data points here. So this is how I extracted the position versus time data from the tracker file. So this is the position in y coordinate of the object, this is the time. So I copied and pasted it in the spreadsheet. I copied the entire thing and pasted in the spreadsheet to obtain the tracker data. Okay. So now let me explain how I modeled this data using VIDLE. So I did two models. In fact, I did three models. The first model I did was to include only the effect of gravity. So in that model I just took the net force is due to the weight of the styrofoam cup, and weight is given by mass of styrofoam cup multiplied by the gravitational field at the location of the cup, which is 9.8 meter per second squared. Since the direction of the gravitational force is downwards and the unit vector j cap is upwards, so I had to put a minus sign to make the weight force downwards. And for the second model, which included the effect of gravity and air resistance, I first used the turbulent drag equation as given in the assignment, which is proportional to the square of the speed of the object. So this is the equation for turbulent drag. So drag force is minus b times magnitude of the speed whole squared multiplied by the unit vector. And if I add this to the weight, I get the net force, which takes into account the turbulent drag. Later when I did for laminar drag, I did it with drag force equal to minus b times magnitude of v into unit vector. So laminar drag is proportional to the speed of the object, and I in fact found that the laminar drag actually is closer to the actual data. The prediction by laminar drag, that is proportional to magnitude of speed, it gives a closer match with the actual data. So I'll be talking about the conclusion, then how I initialized the data, how I adjusted the parameters to fit the data, and all these things I'll cover. What if question, what does it mean question, everything I'll cover one by one. So let's move on to the code. So let me explain my Python code. So these are all the default things which are already present. Okay, here is where I am setting the initial conditions. So mass of the cup is 0.5 grams. So here, since everything is in SI units in kgs, it becomes 0.005 kgs. And these hash tags I have added to change the values of the mass, because I did the experiment by adding one paper clip to this to check whether my model is predicting what will happen if the weight changes. So in that case I will put a hash here and remove this hash so that I can change the mass. Okay, but that is not required for this particular lab assignment, so we will not go into that. Next, the initial position of the styrofoam cup is at the origin, so I have set it to 0. Initial velocity is also 0, so I have set this vector to 0. This line I used when I set the initial velocity to minus 1.4 meter per second. So in this trial, since I have taken it to be 0, I am going to use this line. And the time starts with 0 seconds. Next, the time step I have used is 0.008 seconds. This is to match with the actual frame rate of my video, so that I get almost the same number of data points as the video. If I decrease it to 0, but when trying to find the actual value of B, I wanted to collect more data points, so I used the time interval as 0.001, but this gives too many data points, so it's better to use 0.008. So then here I initialized the unit vector for velocity. I went to the Python website and found out that whatever is the velocity vector dot norm will create the unit vector automatically. So I use this function. So cup dot well is the velocity vector, and dot norm of that will give me the unit vector of that vector, velocity vector. So that is how I defined the unit vector as v hat. Then the proportionality constant I took to be, so initially I started with some random number b equal to 0.003 say. Then by trial and error I run the program many times till the final position matched with my experimental data. So that's how I arrived at b equal to 0.00325. So first we will model without drag force. So I have set b equal to 0 for now. Then g value I set to 9.8, and the unit vector for y-axis I have defined here as 0, 1, 0. So the y coordinate alone is 1, so it's a unit vector in y-axis. This is used to make the gravitational field into a vector, the acceleration due to gravity a vector, so or the weight force into a vector. So weight I am calculating as the mass of the cup into g. G is just a number, so far mass into number is a scalar. So to make it into a vector I have to multiply it with j hat, which is a vector. So scalar multiplied by vector gives me a vector. And the drag force initially is set to be 0, so the net force is also initially set to be 0. Then in these lines I am writing the output. This time I have added the, in my spreadsheet, in the CSV file which is generated by running this program, it is going to give me the time, position, velocity, drag force and net force as a function of time. So these are the values: cup dot pos dot y and velocity, drag force, net force. All the y components I am capturing, but in the output window it will print only the time and y position. So the graph also will plot only the y position and time. Okay, now comes the programming part, the actual functionality. So I have set the time limit till the last time instant of the, till the time of the last frame in my video, which is 1.58125 seconds. So drag force is the turbulent drag. So here I will explain the equations for both. So initially here let me show you for turbulent drag. So I will make this hash and this I will remove. Anyway, for the first trial, which is without drag force, I have set b equal to 0. So even though this code is active, the drag force calculated will still be 0 because b is 0. Anyway, so here the way I calculated the drag force is minus b into cup dot well dot mag2. Again, this function I got from the Python website. So mag2 will give you the magnitude of the square of the vector. So the vector here is cup dot well. So dot mag2 will give me the square of the magnitude of cup dot well. So that magnitude into b will still be a number, so I convert it into a scalar by multiplying with the unit velocity vector, which is v hat. So similarly for laminar force, I don't want the square of the magnitude, I want only the magnitude. So I multiply it with just b cup dot well dot mag. So that's about how I calculated the drag force using Python. So next I am going to calculate the net force. So I just add the weight and drag force which I calculated in the previous step. So the new velocity is the old velocity plus acceleration into time. So acceleration is net force by mass. Net force was calculated here as the sum of the weight and drag force. So now I have to update the velocity unit vector. So unit vector I am updating with the latest velocity value. So v hat is equal to cup dot well dot norm. So this updates my unit vector after each iteration, so that in case in my simulation the velocity is going to change direction, then my v hat will get updated with the new information. So then position vector is, new position is the old position plus the current velocity into time. So this gives me the new position vector. So now I am also incrementing the time by delta t, and I am writing the updated time, position, velocity, everything, drag force, net force, all the y coordinates of that, y components of that. So rate 200 just makes the simulation run at a decent speed. So that's it. So this explains my Python code completely. So now let's see how the tracker how the code works. So let me run it. So this is in the absence of drag force. I had set b equal to 0, and you can see it's falling and it's accelerating, the position is increasing, and the velocity appears to be increasing at a constant rate. So this is the typical free fall. So the final position is pretty high. It has fallen by around 12.3 meters. So now let's include the turbulent drag force and see what happens. So instead of b equal to 0, I am going to make b equal to 0.00325. This was the final value which I arrived at by trial and error. So as you can see, the it appears to have attained a constant velocity. The slope is more or less constant. So this is how I manipulated the values and did all the trials. Now I'll quickly discuss all the graphs, the output, final outputs. So this is the data with the drag force. This is this is the actual data from the tracker of position, y coordinate, and the time. So when I plotted it, so this is the position versus time graph. The black dots are the actual data from the tracker, and this blue line is the predicted data from my model for turbulent drag force with a b value of 0.00325, and the green line gives the predicted data of when the drag force is laminar, that is, it's proportional to the magnitude of the speed and not speed square. So as you can see, laminar drag seems to be a better fit for this data than the turbulent drag. But this deviation is visible only when I plot it in such a magnified manner. If I add the position for the prediction of zero drag force into this graph, then we can no longer notice this deviation. So I'll show you. See here, this red line is the zero drag force, that is only gravity is present. So now the other three graphs have come very close, and it seems like my model is actually a very good fit with the experimental data. So we can't be sure how good it is unless we know the error bars in my tracker data. So if my model lies within the error bars of the tracker data, then we can be sure that our model is a good prediction. Okay, next next we need to know what is the unit of this drag coefficient B. So I have derived it here. So we know that the net force, we know that the drag force will have a unit of newtons, so which is mass times acceleration, so kg times meter per second squared. So and the unit of velocity would be meter per second, so since it is velocity squared, it would be meter squared by second squared. And this is unit of B for turbulent drag. So the unit would change for laminar drag. So the unit of B becomes kg per meter second for turbulent drag. For laminar drag, it would be kg. So for laminar drag, the drag coefficient B would have the unit of just mass, that is kg. Now to answer the what if question, so we can see the answer in this graph. Here I change the initial velocity values for the different so I set the initial velocity value to 0 meter per second, and that is this graph, this blue line. So it started from 0 velocity and the speed started increasing in the downward direction, but the slope of this graph is decreasing, which means the acceleration is decreasing. Finally the acceleration became 0 here. So this is where it reaches the terminal velocity. So it's 1 point something, 1.4 something, and when I change the initial velocity to -1 meter per second, so it started from -1 and again reached the same terminal velocity value around the same time, approximately the same time. Now if I change it to -2 meter per second, it started from here. So now we can see that the slope is in the positive direction. That means the net force was upwards. That means the drag force was greater than the weight of the object initially, and as a result the net force was upward and it was slowing down. But the sign of the velocity is still negative. That means the styrofoam cup is still falling down only, but then it is slowing down, and the acceleration is also decreasing. The magnitude is decreasing, the slope is decreasing till acceleration magnitude became 0. So again it reaches the same terminal velocity. So if I start with even greater initial velocity in the downward direction of -5, the acceleration is even much greater, so it quickly reduces to the terminal velocity value. It approaches terminal velocity almost after same time in all cases. So this seems a bit counterintuitive. We would think that if you start with greater downward velocity, it should take longer time to reach terminal velocity. But what happens is, if you start with greater initial downward velocity, the drag force is also much greater, so that the upward acceleration is also much greater, so that it slows down even quicker and again reaches the terminal velocity around same time. So this answers the what if question. Next we will answer the what does it mean question. So I have plotted the velocity versus time with drag force, which is the red one. As you can see, the velocity the slope of the velocity versus time graph decreases till it reaches 0, and after that the velocity remains constant at terminal velocity. Whereas if you don't include drag force, then the velocity keeps on increasing in magnitude, so it keeps on accelerating at a constant rate. The slope is constant. Slope of velocity time graph is acceleration, which is constant and negative. That is 9.8 meter per second square. That is this green line. So that completes my report. Thank you.